So, as Professor Bill mentioned, this is the MP3 steganography group, Gentiana, Michael, and I, that have been working for the last 2 semesters. So we'll jump right into the problem. So steganography, as we know, is the art of hidden writing, so that people can use steganography to hide files, messages inside another file or message, so that other people do not know about the existence besides the intended recipient. MPEG audio layer 3 is more commonly referred as MP3 and is the audio encoding format for the digital audio files. So the main task we had to do during these 2 semesters was to try to hide data or information inside the MP3 file and inside the main data portion of that MP3 file, while keeping the file size unchanged and also preserving the audio quality so that there will be no sound artifacts introduced. There are primarily 2 MP3 steganography techniques which can be used to hide the stuff inside the MP3 files, and those can happen during the encoding process and also the post-encoding process. We will talk a little bit more about the during encoding process, and while the other technique, the post-encoding process, makes the use of some of the, let's say, some bits that are not really used by those MP3 files, which can reside in the header, site information, and also other sections inside that MP3 file. You can also use the frame replacement, which takes out the frame, which contains the main data portion, and put your stuff in. So you replace the actual main data port with your stuff. So the first thing we had to do was to learn and understand the basic structure of an MP3 file and how the MP3 file is organized. Each MP3 file can start and also end with an ID3 tag. So you can see this on the top and also in the bottom, the ID3 tags. These contain some information about that MP3 file. Let's say, for example, they contain some metadata like the gender, the author, also the published year, etc. But these are mainly optional, and some MP3 files have those tags, some don't. And then each MP3 file is divided in some small blocks, which are called frames. And we can see that we've listed frames here, and each of the frame contains of 5 parts. They can contain up to 5 parts. They contain the header, CRC, the site information, the main data portion, which we will be playing with, and also the ancillary data. So the header is 4 bytes long, and it contains some bits that are really important when we want to decode an MP3 file. So it contains the synchronization word, which can serve as a reference when we want to decode an MP3 file, which serves to find where the frame stores within an MP3 file. After that, there is also a protection bit inside the header, and if the protection bit is set, there will be a cyclic redundancy check right after the header. So that is 2 bytes, and it does the checksum of the frame. It sees if the frame is corrupted or not. The site information is the main part when we want to decode an MP3 file, and its size varies, because if it is a mono MP3 file, then it will be 17 bytes. And if it's a stereo, it will be 32 bytes. The main data portion, which you can see in the green here, and also the ancillary data, which doesn't really contain useful information. It can contain some leftovers from the main data part. So while there has been a lot of work on the MP3 steganography, there is not much done into trying to hide stuff inside the main data part. But I made sure that we've listed some of the projects that did this. One of the projects that does and tries to hide the information inside the main data part is the MP3 Stego by Fabian Pericolas. So this happens during the encoding process, and it takes a WAV file as a source. It has also some limitation because you cannot save a lot of stuff inside it. MP3 Stegosaurus is a tool that was developed here in IIT by one of the former IIT students, and this plays with other parts of the MP3 file. It doesn't touch the main data port. So he makes the use of some bits that are not really used by these MP3 files, or that just the MP3 file ignores those bits. For example, some bits that are inside the header or also inside the site information. MP3 Stag was the project that was developed here at IIT also last year. Jalene and Ben had the same task as we had this semester. So they had to try and see if they can hide information inside the main data port of the MP3 file. Actually, they did develop a tool which they called MP3 Stag, and all the Windows Media Player or all the players that they tested those files worked well. They played the file, but somehow they introduced the sound artifacts which you could be able to easily hear. So since we're playing with the main data port, we had first to see how it's structured and how it's organized. We can see from the screens that the main data port is divided into two granules. And each one of them, it contains channels, the left and also the right channel. And each one of the channels, it contains the scale factors and also the Huffman coded bits. The scale factors are used inside the main data port to reduce the quantization noise, while the Huffman coded bits contain actually the audio data inside that MP3 file. So this is pretty much what it looks, the main data structure. And usually they are divided into three sections: the big values region, the count one, and also the R0. So the R0 region contains some bits that are already quantized to 0, and they do not contain some useful information about the MP3 file, or they do not contain actually the main data inside this region. The count one, which will be encoded in 4 variables at a time, and the big values region, which will be encoded in pairs. So this is the part 2-3 length, and this is the place where Petticola's project does hide the information during the encoding process. It was really challenging and important to know exactly where the main data starts within a frame. So here you can see from the screens, we represented that this is the header, this is the side information, and the main data port in green. So we can see that the main data port inside one frame can end before that frame ends, but it cannot go forward. So this is the leftover that is reserved for the main data port of the frame 2, as you can see here from the screen. And this is because of the bit reservoir, which is a feature in those newest MP3 files. I think, and Michael is going to present the solutions that we analyzed, and also Gentiana for the tool we did.
Okay, I've never really had a problem being heard, so I'm not going to use the mic. I want to save your eardrums. So if somebody does have a problem hearing me, though, let me know, and I'll speak out. Is that bad? Take the microphone. You take the mic? Oh, you have to have the microphone, huh? All right. Is this better? Hello? Is that working? I think so. Is that working? Okay. All right, so second, as Adrian said, my name is Mike. And we're going to discuss a little bit about our journey from September last year. So up on the board now, you're going to see some of the things that we wanted to try when we first started in September. In September, we were very motivated, very happy, very excited, and we had all these great ideas on how we were going to make this work. By December, we were pretty beaten down and sad. But one of the first things we were talking about, masking our hidden data. If you don't know about MP3s, one of the things that happens from studio quality audio down to the MP3 level is there's a lot of compression that happens. So one of the things that happens during that compression process is the MP3 encoder is going to remove those sound waves that aren't going to be heard naturally. Okay? So picture yourself in your car driving down the road. The semi drives by you and you don't have a sound or the radio on, you're going to hear that semi drive by. But if you have your radio up and you're cranking some tunes, you might not hear the semi go by, okay? That's masking. So MP3 encoders are going to remove the sound of that, the semi going by, because it's unused data. It's not necessary. So what we thought is if we wrote our own encoder, we could leave those sounds in, okay? And then we would use those sounds to actually mask our data, and that way it would all be part of the MP3. It would be encoded. It would be very hard to detect. What we realized is we'd need like 3 years to figure this out and code it. So it wasn't going to happen in a 2-semester project. So then we decided, okay, let's try the least significant bit. It works in JPEG steganography. Maybe it can work for us. Again, we wound up with the same issue. We were trying to build a custom encoder. this was the bane of our existence. We looked at this code, we looked online, we looked at encoders, we dug into them, and what we really came to realize is when it comes to trying to build your own custom encoder, you need a lot of time to figure it out. So basically the idea behind least significant bit is that we're going to take a byte, and that last bit in the byte is not really necessary. You can change it a little bit, and it won't really affect the outcome of the sound. But again, the only way we could make this work is to write our own encoder, and we just didn't have time to do it. So then, overwriting the main data of the data portion. This is where we really started to spend our time in December. We were just going to go in there and try and alter a few bits or a few bytes of the frame and say, okay, maybe that won't introduce too much sound artifacts. And we had some success with this. And unfortunately, we had it early on. We encoded we took an encoded MP3. We changed a few bits, like about 10 bits at the end of a frame, and you couldn't tell. It was awesome. We were like, yes, we're geniuses. But what we realized is it was only that one encoder that was used. So we had downloaded all of our practice files from the same website, and of course they used the same encoder, and that encoder allowed us to change the 10 bits without a problem. But as soon as we went to other websites and started using other MP3s, we realized that it wasn't the solution, and there were a lot of sound artifacts being put in. So we moved on from that to changing the CRC bit, which is the correction bit. And basically what we thought here is, if we change the correction bit and we say, you know what, make this think that this is a bad frame, okay? And if it's a bad frame, maybe the MP3 player will just skip it. Then we can bet all the data we want into that frame, and nobody be the wiser. This didn't work out very well either, and it actually introduced more sound artifacts than overwriting the main data portion that we tried. So then we went to inserting and using the existing frames, empty frames, and that's where we're at today. And later on, Gentiana is going to tell you how that worked out for us. So I kind of gave you an overview of those different things. So overwriting the main data portion, like I said, those first two kind of got excluded after about 3 months of trying different things. We couldn't build the custom encoder, so we went to this. So our plan was we're just going to overwrite a portion. So we started out with 10%, 20%, 50%. We didn't touch anything in the header or didn't touch anything in the side information because that was our project. We had to do it with the main data portion of the MP3. So this was our first tool. You can see kind of how it works. We have right here, that top line right there. That's the MP3 that we're going to embed into. So that's the clean MP3. Hasn't been altered yet. This next line right underneath it, browse covert file, that's going to be what we want to hide inside of that MP3. Now, the tool itself would then populate these next 4 boxes down here, which is the MP3 length, MP3 playtime, covert file length, and the number of frames. The big thing for us was the number of frames, because the more frames that we had, the more data we could probably put in there. Then coming down below that, in the hiding parameters, we had a starting frame, and that starting frame would decide where in the MP3 we were going to start at. So we might not want to start right at the beginning, because starting at the beginning, the sound really hasn't gotten moving yet, or whatever the MP3 was. So we decided we wanted to be able to start somewhere inside of that MP3. So maybe 100 frames in, 200 frames in, whatever else. So we wanted the ability for the user to decide, okay, I want to put it in this far. So that starting frame is where we're going to start embedding the information. The number of frames in between, that's the number of frames that we're going to remain unaltered in between our altered frames. So let's say we started, like in this example, we're starting with frame 2, and then we're going to skip 30 frames. Then we're going to alter that frame. Skip 30 frames, alter that next frame. And then how much of the frame do you want to overwrite? In this example, we put it at 100, which obviously didn't work out very well. But even if we went down to 10%, 5%, it still didn't really work out well for us. And then finally, over here, where it says where to hide or where to insert that data, we gave them the option that they could put it at the beginning of the frame or at the end of the frame. So I believe the next slide is going to show you the results of that. Yeah. So we tested this, and like I said, right away early on, we got great results because we downloaded everything from the same website, and you couldn't hear a thing. But then after we practiced a little bit more with it and tried different websites, we got these results. So the original sound. Okay. Technical difficulty. We just just want everybody to calm down, relax. Kill the projector in the middle of the presentation. This is good, isn't it? Okay, so this is the other one. You can hear the artifacts that are being put in there. We don't need visuals. You can just hear it, right? So you could hear a lot of those artifacts were put in there. Like I said, early on, we didn't have the issue, but when we started to try the different MP3s, we started to get, can we back it up one? Or?
Yes.
We started to get a lot of those artifacts. And as you can see here, these were the settings that were used in this example. So we started at frame 20 because it started out kind of quiet, that MP3. So we wanted to go in a little bit when we started embedding the information. We only put 2 frames in between that were untouched. And then the number of bytes that were overwritten, we were only overwriting 6 bytes at the end of a frame. So we kind of thought, okay, well, this is a minimal amount of data. We should be good. Like I said, you could notice it very easily that there were a problem with it. So then file structure matters. So how the MP3 itself is constructed had a difference in how things worked. The encoder that was used to encode that MP3 made a difference. So generally it worked only with certain MP3 files, as I said. One of the things that we also ran into, we noticed that it was the lame, what was it, 398.2, right?
Yes.
Lame 398.2. That encoder, for whatever reason, only uses one channel. Even though it says it's stereo, it only used one channel of the MP3, which left the other channel completely empty, and we were able to do anything we wanted with it. So we were dumping thousands of kilobytes of data in there going, work, awesome. But again, it was only that one encoder that worked, okay? So 10 bytes seemed to be the limit on some of the other MP3s we ran into. When we overwrote more than 10 bytes, it became very evident. And then, like I said, as soon as we got to some of the other MP3s, it was evident no matter what we did. Even 1 byte made a difference. Other MP3 files changing the same number of bytes at the beginning or the end of the frame introduced that same disruption that you heard, and it was very noticeable noise. So then, like I said, the CRC bit, the hypothesis was, like I said, we changed the CRC bit, and then the player itself would just ignore that frame. It would say, okay, it's a bad frame, so whatever's in it, we're going to ignore it. And it will mute that frame or replay the previous frame. So testing the hypothesis, modify the protection bit, set it to 0, which means it's CRC protected, and then overwrite the main data of the modified frame. Obviously, it wasn't going to match, and it was going to say, okay, this is a corrupt frame. This wound up with more distortion than it did on the others. So by not changing that protection bit, so we wound up not using this idea either. We could not modify the CRC bit or code. So then overwriting the main data, we came back to this. One of the things that we figured was it was that bit reservoir. So we're only changing a few bytes at the end of a frame, but that doesn't mean we're actually changing the end of the frame. Because if you remember the bit reservoir, if you look right here, we could be changing this little bit right here at the end of that frame, but we could actually be changing the middle of the frame after it, because with a bit reservoir, you can have part of this main data frame being written in the frame before it. So, and because that's going to span throughout the entire MP3 player, or the MP3 file, you could wind up changing the middle of a frame rather than actually right here, which is what we wanted to do. And the only way we could actually try and get to the end of the actual main data portion of the frame would be to, again, write our own encoder. Because we'd have to go in, we'd have to decode everything, get to the actual main frame, overwrite the bits we wanted to, and then put it all back together. And again, we're talking years and years of trying to develop that. So we weren't able to follow through on this. So, and I want to point out, all these great ideas we had are possible. We still think they're very possible. We just don't have the time to work on them. So if anybody really wants to go for it. So changing a single bit at the end of a frame can disrupt several frames. Cannot add a frame unless it's at the beginning or the end. Again, the bit reservoir. If I add a frame in the middle, I could be splitting the actual frame because that main data could have been in the frame before it. So I couldn't just add, we couldn't just add frames in the middle. And we couldn't remove a frame for that same reason. We could have a little bit of the frame in the frame before it and would screw up the MP3 again. So the bit reservoir is really kind of a pain in the butt. So then we came down to the empty frames. So with the empty frames, they're at the beginning and the end of an MP3 file. And the way it seems to work is the MP3 file takes those first few frames to synchronize, and so it doesn't really care what's in them. So most MP3s will have empty frames at the beginning and at the end, and then we could add some more empty frames at the beginning or the end. And what we do is we didn't change the header and we didn't change the side information because those things, the header and the side information, are what the MP3 player uses to synchronize. So we don't change those, we just change the main data portion. And that allowed us to take 3, 6, 8 frames worth of data and store it into the MP3. And Gentian is going to go into that in a little bit more detail. So as I said, the first few frames are for synchronization, usually 2 to 3 frames. We could add some more empty frames, and even if some MP3s don't even have empty frames, but we found even if we add empty frames to those MP3s, the player still ignores them and synchronizes with it. So again, there was no real artifacts or results, or negative results. So using empty frames to store data, modifying the empty frames doesn't introduce sound artifacts. Not empty MP3 file has empty frames. We would be very limited on how much data we can store is one of the issues. And this technique will be a carrier dependent on storage capacity. So depending on how much data was stored in a frame would depend on how much we could store in that empty frame, or how much data we could actually store. And if there were no empty frames, it might not be possible to store the data. And Gentian is going to go into this in a lot more detail.
Okay, so to overcome the issues that Mike just talked about, our solution was adding some extra frames to the MP3 file. And because of the bit reservoir feature, we were limited on the place where we could actually add those extra frames. So we could only add them in the beginning of the file, before the very first frame, or at the end of the file after the very last frame. So what's the issue if we do that? Well, the problem is, as you can imagine, that if we are adding frames, we are increasing the file size. Therefore, we cannot add a very large number of frames because the file size will be increased in that sense that everyone seeing the MP3 file will notice that there's something wrong with that. So our current implementation does that, just adds 3 frames at the beginning of the file and 3 frames at the end of the file. By doing so, we are just adding 6 extra frames, and that's, if we translate it into seconds of play, it's 1/10 of a second, so it's not even a second of play time. And usually it's less than a kilobyte. But we are really, what we always cared about is how much, even if we are able to store data inside the MP3 file, how much data we are able to store. So we came out with some calculations. So the capacity depends on the number of existing empty frames, since we are going to use them, on the number of added frames. As you know, we are adding now 6 frames, so this number is already known. And then on how many bytes we can modify in one frame. As Mike was saying, we are not changing the header nor the side information, because if we do so, the player might corrupt the entire file, and it will just refuse to play the MP3 file at all. So the capacity is, the formula to calculate the capacity is this one here, and I'll tell you with an example later on. So what's the important thing about this? That we are going to be able to store some data even if an MP3 file doesn't have empty frames. So even if the existing empty frame is 0, we still have those 6 frames where we can store our data in. So that's why we built the tool, that's the secret MP3 tool, which does embedding the covered data into the MP3 file, as well as retrieving the covered information from the carrier MP3 file. And during the embedding process, or in the embedding mode, we need to provide the tool with 2 inputs. That's the clean MP3 file, and the other one is the covered file, for the moment a .txt document. So the process on how the tool does the hiding is as follows. It first generates the empty frames. It goes to calculating the maximum storage capacity. And then this is a very important number, since we need to know what's the maximum size that we can store in. So when we receive the covered file, we can compare those to the maximum storage capacity and tell the user whether we are able to store that text document or not. Let's say that the maximum storage capacity is 5 kilobytes, and the user wants to store a 10 kilobyte file. So we're just going to tell him that, sorry, but this MP3 file is not able to hold your covered information. And then after checking if the covered file is within the size, then we are going to create that master frame, what we call. The master frame contains the necessary information that we are going to use when retrieving the covered information back. And then after the master frame is created, we are going to just embed the covered file into the MP3 and then create the what we call the dirty MP3 file that contains the hidden information. So, well, our approach would be useless if we would just be able to store the data but never retrieve it back. So the tool is able to run in the retrieving mode, meaning that it's able to have a MP3 carrier file and then retrieve the covered information that has been hidden previously, of course, with our tool. The process is more simple since we only need one input, that's the carrier MP3 file. And the process is as follows. We first read, the tool tries to find the master frame. And then when it finds the master frame, it reads it and it extracts the necessary information. It needs to know where the covered information has been hidden. And after finding that, it just retrieves the covered data and gives back that to the user. So that's a simple GUI interface of our tool as for now, and it's running in the embedding or hiding mode. So we just need to input the MP3 file, and then here is the covered file, and then just the button hide, so we can hide the data. These are some little stats that we want to put so that the user who's using the tool can know what's the important number here is the maximum payload size. So what's the maximum size of the carrier file that can be hidden inside this MP3 file? So we see that there are 76 existing empty frames. 6 are added by us. So the maximum capacity is, as you see, it's a little bit more than 31 kilobytes. And, well, we've been testing quite a lot, especially after getting those false positive results we were so happy about. And then after coming up with this solution we are presenting today, we've been testing with several MP3 files, making sure that we are downloading them from different sources and using different media players. So we'll just listen to those files and see whether we can notice a sound artifact or not. And so far, we haven't been able to notice any sound artifact introduced in those. But the only drawback is that the size increases slightly, and that's usually approximately 1 kilobyte. But in blind steganography, you won't have the original MP3 file. Therefore, just 1 kilobyte change in the size won't really matter, because the person who is analyzing the file will have only the dirty MP3 file. It won't have the clean files, so he can compare. What we really want to do in the future, since for now we are just inserting the covered file as a plain text, we are thinking of encoding, maybe base64 encoding. So we just would escape kind of some easy step analysis techniques, and then maybe introduce compression and encryption, so our steganography technique would be more secure. Now I'll just walk you through a quick demo on how we do the process of hiding and retrieving covered information using the secret MP3 tool. So we first will just run the tool. And as you can see, so it has the hiding and recovering mode. We are in the hiding mode. We are going to browse the MP3 file. There we should browse the covered file, and then the button hide is used just so we can hide the file. We are using the Anthem of Republic of Kosovo, so that to be our carrier file. And then here we see the stats on the file size, the MP3 playtime, the number of frames, and all the stats that we see. The most important, as you know, I stated before, is this one, the maximum payload size. So having this, now we can browse our covered file and input it. So we have some covered tags there. We will just open for you so you can see what it is. It's nothing bad. It's just an assignment there. So it's a simple TXT document. So it says that the covered file was set successfully because its size was just 5 kilobytes, while we would be able to store there 31 kilobytes. After pressing hide, we see that the Stego file has been created. And we see here the name is, we just use the same name underscore carrier. The size has increased for 1 kilobyte, while the length didn't increase because by adding 6 frames, we are just adding a tenth of a second. So that was the original file, and let's hear the other one that we changed. As you could see, they sounded all the same, but we just want to give you a hex view of the covered information that we have changed. So we'll just open the carrier file. So we'll open the carrier file we just created, and we'll see how it looks like. As you can see here, this is the master frame. So the important information we use to retrieve the file. And this is the entire assignment saved. So even though this whole stuff was inside the MP3 file, we just we couldn't hear that there was a difference. So we are just scrolling through the MP3, and you can see, like, here the MP3 data really starts. And also at the end of the file, there is the other part of the assignment, which we've been able to store it successfully. The trick here is that the MP3 player will just ignore those frames where we have stored our data in, because of the header and side information tells it to do so. So you would be able to store quite a lot of information, especially if the MP3 file has empty frames. But even if it doesn't, if you insert those files, you would still be able to store lots of data. So now let's just go back to the recovering mode, and let's retrieve the hidden information. As an input, we have to give the carrier. So, and it's simple. We just press retrieve file. The covered file was retrieved successfully. That's the message we get. And let's see now the retrieved file. It's the exact same file which we just hide there. Well, by using this technique, we may be able to insert even more information, but that would increase the file size quite a lot. So thank you. This was our presentation. And
Questions?
yep. So,
Any questions?
yep.
Comment more than anything. It's interesting because throughout the years of everyone downloading music from back in the day and now, you come across a lot of files that are fake, that normal people would think they're fake, with either clipping noise or, you know, just dead air in the beginning or after. So it's interesting because people could have done this for quite some time, if you think about it. Because no one would even think, they'd be like, oh, this file is garbage, next, let's download another one. So, I mean, it's interesting, because I would have never thought about that. I would have deleted it and said, okay, next.
Yeah, it's very possible that it could have been, yes.
Yeah, it's pretty cool.
I think there was one in the back, and then we'll get to you, sir.
So is there a way to not put this extra 6 frames on it? Like if I have a file that I know for sure it has some empty frames and I just want to use those, is there an option to do that with your tool?
Currently, in our current implementation, not now, but yeah, we are planning to do that. Because, yeah, that would be more efficient since we wouldn't add extra frames if we already have enough space. But as you saw, the file we just presented was kind of it had quite some frames, but the other files usually have like 2 to 3 frames, maybe maximum up to 10 frames, but not more. So yeah, we would definitely, that should be our future work. Thank you.
Sir?
Yeah,
Oh, I'm sorry. I was. Okay, go ahead. Sorry.
Yeah, have you looked into the possibility that the frame you insert may not, the signature of that frame may not match the normal MP3 frame, so people can easily detect that it's a frame you insert?
Yeah, that was our concern at the very beginning, but the very first few frames of the MP3 file, even if they are not empty, they will be ignored because they are used to synchronize. So we are like copying the very first frame and then duplicating, in fact, like replicating it 3 times at the beginning and 3 times at the end. So it's a correct MP3 frame.
Right, I understand you visually, by AI you cannot detect, but you try to defeat people, try to deliver some information so people cannot detect you are sending information. So the frame you are sending, and it should be similar to the MP3, regular MP3 frame.
Yes, in fact, the header and the site information, it is 100% the same as a regular MP3 file, while the main data, yes, if we do a statistical analysis, then yeah, it can be detected by that, because there might be like a pattern that every MP3, the main data in the MP3 file can have, and our frames that are modified won't have that for sure, because we are just like inserting all the data we have.
But there is potential. We could try and do the Hoffman encoding on it to make it look similar, and if we use the same Hoffman tables as the MP3 table or the MP3 uses, we could mask that data a little better in the main data portion. So there are different things we can do, and that's what Jetiana was talking about during future work. It's just when you're dealing with MP3, it took us so long just to get our head wrapped around what is an MP3 and quantization and Hoffman encoding and all the different aspects of it. When you really try and get into hiding that data where nobody's even going to know it's there, you need a lot of time and a lot of work to be able to do it. So the 2-semester project just wasn't going to allow for it. But we do have concepts and ideas on how we might be able to mask it better to defeat some of the stake analysis tools that could be used against us.
And also we can introduce the encryption in the future, so that will make more difficult for people out there to see it just as it is right now as a plain text inside the main data portion of that MP3 file.
Yeah, they might know it's there, but they might not be able to tell what it is. So, sir, I'm sorry.
My question's answered.
Oh, was it? Okay. I'm sorry, sir.
The 2 files, the one, the original, and the one after you did your inserted the document in there, if you did a hash on it, would the hash both be different? The hash would be different.
Absolutely.
Yeah.
But then again, it's a blind analysis, as Jetiana said. So normally you're not going to have that original MP3. And we were actually discussing this in class the other day. With the nature of MP3s, and there's so many different versions out there and different things out there, it might be possible for somebody to find the original. So if you truly wanted to make it so that people would have a blind steg analysis on it, you'd have to create your own MP3, because then nobody would ever be able to get the original. But without the original, you'd never be able to compare the hash.
Well, sometimes you have these audio programs where you can actually cut your MP3 into pieces, and so the slides are going to change anyway.
Right.
You start doing that.
Exactly. And, there could be 8 different versions of the same MP3 out there. I'm sorry. Yes.
So I've seen that the file, the hidden information is the file size was 5 kilobytes, right?
Yes.
But the file size of the carrier increased by 1 kilobyte. So
Right.
how is that possible? I mean,
Okay, so reason behind that is because we are using the two types of steganography techniques, insertion and substitution. Insertion in the sense that we are inserting those extra frames in the beginning and at the end, that's approximately 1 kilobyte, and substitution because we are modifying the content of the empty frames with our data. So that's why the size didn't increase 5 kilobytes, but just 1.
Yeah,
There were
actually,
already empty frames there that
Right.
we were altering.
those are already there, so they're existing there, so we'll make the use of them.
Any other questions? Yes.
So, so you could, if you were, let's say a blind test, you don't have any, the original would be something that you created just by chopping up 15 different national anthems and, taking 10 seconds each or something like that. You could then actually put an arbitrary amount of empty frames in there for more data than the original source.
Well, at a certain point, the MP3 player is going to actually start trying to play those frames.
Okay.
So we only have a set amount the first few frames to be
Okay,
able to do it.
So the empty frames, there's some.
There is a limit. Yeah, we can't put an infinite amount in the beginning
Okay.
and the end.
It's not marked. It says this is an empty frame. You should ignore forever.
No, yeah.
Okay.
We actually were hoping, we tried to find that, and we couldn't find that
Yeah.
either. So.
It would be a strange thing to add.
Yeah.
Well,
Like, please stick it on.
The issue is you can put them in the middle except for the bit reservoir.
Right.
Yeah.
Which destroys you.
Right.
Yeah, it's a real pain in the butt, as I said.
Without having to entirely engineer the whole thing.
Right. Any other questions? All right, well, thank you very much for your time.